at level 60, it's really just a review of what we've been doing. But here are the steps written out for you on how to solve these equilibrium problems, especially when you're given initial concentrations and you need to find equilibrium concentrations. So we only have two examples, which are going to be the bulk of the level 60 notes, but it's just going through these problems two more times. Okay, so for example 8, suppose for a synthesis of hydrogen fluoride forms hydrogen and fluorine, 3 moles of H2 and 6 moles of fluorine gas are mixed in a 3-liter flask. Assume that the equilibrium constant for the synthesis reaction at this temperature is 1.15 times 10 to the second. Calculate the equilibrium concentration of each component. So the first thing we need to do in this problem is we need to write the balanced equation. Okay, so we have hydrogen gas, and so that's a diatomic, is added to fluorine gas, so that's also diatomic, to form our equilibrium arrow, hydrogen fluoride, and so that's +1 - 1, so that would be HF. Okay, now we need to balance it, so we need to put a 2 in front of the HF to have that balanced. Okay, so that's step 1. Step 2 is write the equilibrium expression. Well, we know that K, I'm just going to write this down now, is 1.15 times 10 to the second. And so if it helps you with your math and typing in the calculator, if you move that 2 times to the right, that's really equal to 115. So that will help out immensely. Okay. Then next, our equilibrium expression. So K is equal to products over reactants. Well, we have HF on the product side, and it has a coefficient of 2, so that means we need to square it over our reactants, H2 times F2, and those both have 1 coefficient, so you don't need to have a unit. Okay, so that's step 2. Step 3, we need to list the initial concentrations of the ice chart in the extract. So initial is our I. Well, for this problem, we are given moles and we are given liters. So we need to solve for our molarity to plug in. Okay? So for H2, it was 3 moles, and it's a 3-liter container, so that would be 1. I'm just going to shorten it for now. We'll do sig figs at the end. Okay, and then, so that will go into my chart, 1 molar. Okay, and for the F2, we have 6 moles to start with in our 3-liter container. So that would be a 2 molar mixture. I'm sorry, 2 molar. Okay, and it doesn't say anything about our product, the HF. So the initial concentration of the HF, if we don't have anything putting in first, it would just be 0. Okay, so that's step 3. Now let's calculate Q, step 4, to determine our shift so that we can write out our change line. Okay, so Q, we're just going to plug in our initial concentrations. And guess what? Since we have a 0 in the numerator, the Q is just going to equal 0. So that means comparing Q to K, Q is less than K, so that means we need to shift right. So our products will be added to and our reactants will be subtracted from. Okay? So now we can go back to our change and figure out our change. Remember, it's subtracting from the reactants and adding to the products. So X, when we plug in X, we need to multiply it by the coefficient. So H2 and F2 both have 1s in front, so that's minus 1x for each of those. But F2 has a 2 in front, so we need to have plus 2x. Okay? And so then now we can write our equilibrium line, including our variable. So we have 1 minus x for H2, and we have 2 minus x for F2, and then just plain old 2x for HF, because we don't need to include the 0. Okay, so next step is we need to plug this into our equilibrium expression and solve for x. Solving for the unknown. So I kind of skipped over 5, but now we're on 6. Okay, so we know our k is 115, so we're going to plug that in, is equal to hf squared, so we have our 2x quantity squared, over x minus 1 times 2, or sorry, 1 minus x times 2 minus x. Okay, so now we have to do some algebra to solve for this. Okay, so I'm going to go ahead and solve out the bottom denominator to make life easier for us, and we're going to get 115 is equal to, let's distribute this quantity squared thing. So we have 4x squared over, and when I did the outsides, insides, you know, all that wonderful stuff from Algebra 1, I got x squared minus 3x plus 2. Originally when you solve it, the x squared's on the other side, but we're normally used to thinking x squareds first, so that's why I changed it around. Okay, so now we need to simplify to get this because we're going to have to use our quadratic formula. Okay, so we need to multiply by the quantity down in the denominator up here. Okay, so then you get 115 x squared minus 345 x plus 230 no x equals 4x squared. Because of all the math, we need to use the quadratic formula, and in order to use the quadratic formula, we have to have everything equal to 0. So we need to subtract our 4x to the other side, 4x squared to the other side. So we have now 111x squared minus 345x plus 230 equals 0. Okay, so plug it into your quadratic formula. If you need to look that up, please do. I have a handy dandy program on my calculator that does this for me from when I was in high school, so I would maybe look and see if you do. I can tell you in class how to find it. But you get two options when you solve for x using the quadratic. You can either have 2.14 or x can be 0.986. Okay, so now we have to do some critical thinking since we have two options for x. Only one of them is going to be our right answer. The one that's the right answer is the one that gives us a positive number when we solve for our h and our f. Okay, because since we need to solve for our concentrations in this line, because we haven't done that yet, we need to compare these to figure out what it's going to be. So, when we're solving for the concentration of the H2, we have to take 1 minus x to give us our concentration. So if we found, let's first try the first number, 1 minus 2.14, we're going to get a negative number. And so that's going to be negative, and we can't have a negative concentration. So that means the 2.14 is not our x. So that means that by default, x is equal to the 0.968. So then we can solve for all of our concentrations. So the H2 is 1 minus the 0.968. So the H2 is 0.032 molar. The concentration of the F2 is 2 minus the 0.968. So that one is 1.032 molar. And HF is 2x. And so that's 2 times our 0.968. And that would be 1.03 molar. Sorry, I read the wrong thing. That would really be 1.936 molar. So there's our final answer. On example 9, we also have to use quadratic formula. So this is just showing you how you can use those. So for example 9, it's going to be a little different where we're using the pressures instead. We can do the same exact thing with the pressures, okay? So assume that gaseous hydrogen iodide is synthesized from hydrogen gas and iodine vapor at a temperature where the equilibrium constant is 1 times 10 to the second. So that's 100. Suppose the hydrogen iodide at 5 times 10 to the negative 1 atm, H2 at 2 times to the negative 10 to the negative 2 atm, and I2 is at 5 times 10 to the negative third atm are mixed in a 5-liter flask. Calculate the equilibrium pressures of all the species. Well, in this case, since we're dealing with pressures, the volume of the flask isn't really important to us. That's unnecessary information. Okay? So we're still going to follow our steps. We need to write our chemical equation first. So we are forming the hydrogen iodide, so that is Hi. And that's from hydrogen gas, and that's diatomic, plus iodine gas is also diatomic, so that means we need to put a coefficient of 2 in front of the Hi. Okay, so step 1 taken care of. Step 2, we need to write the equilibrium expression. So because we're dealing with pressures, it's really going to be a Kp this time, and that's okay. All right, because we're going to plug pressures into our equation. So it's products of reactants, so it's the pressure of the Hi, and it's squared because there's a coefficient of 2 in front, over the pressure of H2 times the pressure of I2. Okay, and let's not forget that K is 1 times 10 to the second, which is really 100 for our simplifying math. Okay, so now that we have our K expression, let's list our initial concentrations. Running out of room. Okay, so initial concentrations are the pressures. And to save space, I'm going to cut off our wonderful zeros at the end of each one, and I'm also going to convert it into decimal form instead of scientific notation. So if it's -1 for Hi, that means that it's 0.5 initially. H2 is 1 times 10 to the negative 2, so move our decimal 2 times left. That'd be 0.01. And then the I2 is to the negative third power, so we move that 3 times, 0.005. Okay? Next, we need to calculate for Q to see how does our equilibrium shift. So we're going to plug our pressures in. So we have 0.5 squared over 0.01 times 0.005. And watch your math, but Q is equal to 5,000. Well, Q is greater than K. So that means this time we're shifting left. I think this is the first time we've shifted left so far. That's okay. So since we're shifting left, that means we're actually adding to the reactant side this time, and subtracting from the product. So it's different than our last example, where I ran out of room, so I'm going to put my C down here. We are now adding to our reactants, and we are subtracting from our products. And we're going to plug in X, our variable that we're solving for, and it corresponds to the coefficients up top. So that means we're minus 2X because of the 2 in front of Hi. So to find our equilibrium concentrations, we need to take 0.01 plus X and 0.005 plus X and 0.05 minus 2X. Okay, so now we need to plug this into our K expression and solve for X. So we have 100 is equal to 0.5 minus 2X quantity squared over 0.01 plus X times 0.005 plus X. Okay, simplifying this out before I just get my numbers for the quadratic formula, because we're going to have to do that again. 100 is equal to, be careful when you're expanding the top, the numerator. It's 4x squared minus 2x plus 0.25. And then the bottom is x squared plus 0.015x plus, and this one I'm going to write in scientific notation because it's a lot of zeros, 5 times the negative fifth. Okay, so when you distribute everything over so that you get, so we need to take this whole bottom and multiply up by 100, and then we have to get the other side to 0, so I'm just going to simplify steps. If you want to see my note packet to see how I worked it out, that is fine. But I got it to be 96 x squared plus 3.5x minus 0.245 equals 0. So when you plug into the quadratic formula, x can be 0.0355, or it can be negative 0.0719. Okay? So at this point, we've solved for x. Now we need to plug in and find our equilibrium concentrations. So we have to think about what is going to give us the best answer. And again, since the numbers are so small, for example, right here at I2, if we were to subtract by the negative number, we would get less than 0. So that means that the negative number cannot be x. So that means the 0.0355 is x. So to find our equilibrium pressures, our last thing that we need to do, we would plug in that for x. So the pressure of H2, you take the 0.01 plus the 0.0355, and you get 0.0455, and it's in atmospheres because that's what the problem said. The partial pressure of the I2, we take 0.005 plus 0.0355 to get 0.0405 atmospheres. And last but not least, our product, HI, is 0.5 minus 2 times our 0.0355, and that is 0.429. So here is our answer. So last but not least, what if k is very small? Sometimes k is so infinitely small that it doesn't really have an effect on our calculations. And when it doesn't have an effect like that, when we're solving for x, then we can reduce our mathematics when we're solving for a variable. So for an example of that, see pages 631 to 632. There is an example on how to do that. But this is the end of level 60, so we only have 4 problems this time because these are pretty involved. So we have 53, 54, 55, and 59. I've been away.